Welcome back to Chapter 1.3, Part 5 of 11. In Part 4, we derived the standard error of the sample mean, sigma, over the square root of n. Now we confront that square root head-on. It governs how fast precision improves, it is disappointingly slow, and it carries a real price tag. We also flagged the assumption, independence, that the whole clean formula quietly leans on. The standard error shrinks like 1 over the square root of n, not like 1 over n. This square root is the most consequential one in statistics, and it is a little disappointing the first time you meet it. To cut your standard error in half, you do not double your sample, you quadruple it. To get one more decimal digit of precision, a tenfold drop in the error, you need a 100-fold increase in data. Priya's boss wants the estimate twice as sharp? That is not 400 claims, that is 800. Precision is expensive, and it gets expensive at a very specific, predictable rate. Let us make it concrete. Suppose the population standard deviation of claims is $12,000. Insurance losses are volatile, most small, a few enormous. With n equals 200, the standard error is 12,000 over the square root of 200, which is 12,000 over about 14.14, roughly $849. So Priya's estimate carries a standard error of about $849. With 5,000 claims instead, the standard error would fall to about $170. Same recipe, same unbiasedness, dramatically less jumpiness, purely because n grew. One warning before we move on. The clean formula, sigma squared over n, leaned on a single assumption from Chapter 1.2, that the claims are independent, so the variance of their sum is the sum of their variances with no cross terms. That assumption is not free, and in insurance it is precisely the one to worry about. A single wildfire does not file one claim, it files hundreds, all correlated, all driven by the same fire weather. When observations are positively correlated, the variance of the sum picks up extra covariance terms. Those terms are positive, and the true variance of x bar is larger than sigma squared over n. The naive standard error then understates the real wobble. Priya would think her estimate is sharper than it actually is. We will not chase this down now, but file it away. The day you see cluster standard errors later in the book, this is the leak they are plugging. The 1 over root. N rate is a best case that assumes your observations carry genuinely independent information. To summarize Part 5, the standard error improves only at the 1 over root n rate, so having it costs a 4-fold increase in data, and one more digit of precision costs a 100-fold. Precision is expensive at a predictable rate. With a standard deviation of $12,000 and 200 claims, the standard error is about $849. And the clean formula assumes independent observations. Positive correlation, like many claims from one wildfire, inflates the true wobble beyond sigma squared over n. We now have two virtues, aiming true and being steady, that sometimes pull against each other. In Part 6, we combine them into a single scorecard, the mean squared error and its beautiful decomposition.